Today we're going to look at this really nice integral that I found on the Math Stack Exchange. And this is going to involve lots of nice substitutions and then a bit of a spicy contour integral at the end. Okay, so let's see what we have. The integral from 0 to pi over 2 of the arctan evaluated at 2 cosine squared x all over cosine squared x dx. Okay, so let's see what substitution we might start with. Well, I think since 2 cosine squared x is within this arctangent function, that's maybe an obvious first substitution. And so that's exactly what we'll do for our first substitution. So let's set t equal to 2 times cosine squared x. But notice that that's going to gobble up this argument of arctan. It's also going to easily gobble up the denominator. But what about the dx term? Well, in order to do that, we need to solve for x, and then we can differentiate. So let's start doing that. So pretty quickly, we'll get cosine of x is equal to the square root of t over 2. And then we can take the arc cosine of both sides. That is the inverse cosine function. So we have x is equal to arc cos of the square root of t over 2. And now we can differentiate, just being careful about the chain rule. Okay, so the derivative of the inverse cosine is -1 over the square root of 1 minus the argument squared. But the argument squared here will be t over 2. Okay, and then we have to use the chain rule, so we need to take the derivative of the square root of t over 2. So notice that's going to give us a 1/4. So we get a half from the square root. And then we also get a half from the argument of the square root, again with the chain rule. And then we'll have times 1 over the square root of t over 2 dt like this. Okay, so there we have our substitution worked out. Now we just need to talk about our bounds of integration. So let's maybe fit that in this orange box right here. So if x is equal to 0, I think it's pretty clear that t will be equal to 2 because cosine of 0 is 1. And then if x is equal to pi over 2, we will see that t is equal to 0 because cosine of pi over 2 is 0. So notice that's going to switch my bounds so that I have an integral from 2 to 0. But that being said, I can switch it to an integral from 0 to 2 by applying this minus sign. And that's exactly what I'm going to do. Okay, so let's see what I have. So we'll have 1/4 and then the integral from 0 to 2 of the arctan of t over, and so let's see, this cosine squared will be t over 2, so that's going to be over t over 2, and then we'll have this bit right here. And so that'll be times dt over the square root of t over 2 times the square root of 1 minus t over 2. So that's without much simplification there. Okay, so now, well, what can we do to simplify? Well, let's see. We can bring this 4, which is out in front of the integral, and use it to cancel this 2 here. That'll leave us with a 2 left over. But then we can split it into 2 copies of the square root of 2 and bring it into both of these square roots. Okay, so we'll have the integral from 0 to 2. We'll have still the arctan of t in the numerator, but then after putting all of that stuff in the denominator, along with this 4, we'll have the square root of 2t minus t squared left under the radical, but then we'll have a kind of a free variable t outside of the radical. So it looks something like that. And then of course we have our dt component. Okay, so next up we're going to make our second substitution. And that's to change this from an integral that's improper at 0. Notice this is an improper integral at 0, given that the denominator is 0 at 0, to an improper integral at infinity. And those are often a little bit easier to work with. And we'll do that via the following substitution. So let's set t equal to 1 over y, but that means our dt term is negative dy over y squared. Let's also notice if t is approaching 0 from above, we have y is approaching positive infinity. That takes care of that lower bound of integration. And then if t is equal to a half, or sorry, if t is equal to 2, we get y is equal to a half. So I got ahead of myself there a little bit. So now it looks like the bounds of integration will go from infinity to a half based off of these changes of the bounds, but I can use this minus sign again to swap them into a more natural order. So let's see, we'll have the integral from 1/2 up to infinity, and then making our substitutions, we have the arctan of 1 over y. Then in the denominator, we'll have 1 over y, the square root of 2 over y minus 1 over y squared times dy over y squared, where again, we ate up that minus sign just as we discussed before. Okay, so now let's push everything in the denominator together and see what we get. So we'll have the integral from 1/2 up to infinity, and then the arctan of 1 over y. This numerator is not changing. And then let's see, I can take this y squared and maybe take one of the y's and have it cancel this 1 over y. And then the other y, bring it inside of the radical, which squares it again and thus simplifies the inside of the radical to something like this. We have the square root of 2y minus 1. Okay, and then of course dy. Okay, so that's where we're at the moment. And now we're gonna perform a round of integration by parts. And that's what's like really so great about this integral is we're using all of these nice techniques. So 2 changes of variables, and now an integration by parts. And like I mentioned, we're gonna end with a contour integral. Okay, so my integration by parts will go something like this. Let's set u equal to arctan of 1 over y. Notice that makes du equal to, well, we're gonna have to use the chain rule here, but when all is said and done, we get minus dy over y squared plus 1. So I'll let you check that with the chain rule. And then I'll let my dv component be the rest. So dv is dy over the square root of 2y minus 1, but that'll make our v term simply the square root of 2y minus 1, again where we're taking the antiderivative via the chain rule. So now we have to recall the standard integration by parts formula that says the integral of u dv is u times v minus the integral of v du. Okay, so let's see what that leaves us with. So we'll have this is equal to, well, like I said, u times v, so that'll be the square root of 2y minus 1 times the arctan of 1 over y. And then, like I said, minus the integral of v du. But notice we've got a minus sign built into this du component, so those will cancel, leaving us with plus the integral from 1/2 up to infinity of, let's see, our v du will be the square root of 2y minus 1 over y squared plus 1. So like I said, square root 2y minus 1 over y squared plus 1 dy. Okay, good. But now let's notice that this first bit needs to be evaluated from 1/2 to infinity. I almost left that out. So if we evaluate this at 1/2, our first term is 0, so that cancels out. If we approach y towards infinity, we get the arctan of 0, which is also 0. So in both cases, this bit just simply goes to 0. So now that means our goal integral over here is really equal to this. And so let's start a clean board with that. Okay, so this is where we ended on the last board. Now we want to make the jump towards an integral involving complex numbers, and here's the way that we're going to do this. So let's think about the entire real number line for just a second. And let's put this number 1/2 on the number line. And notice that on the open interval, or on the interval from 1/2 to infinity, the integrand here, the function that's being integrated, is real. So let's maybe shade this in yellow, and we'll notice that the integral is totally real in that component. But notice if we're to the left of 1/2, and so if we're strictly less than 1/2, then the argument of the square root is negative, and so the integral is imaginary. In other words, well, the function is imaginary. So that means that we could exchange the bounds of integration here for a complete integral over the real line and just extract the real part. Because upon introducing the rest of the real line, we've only introduced imaginary part of this integral. Okay, so after all is said and done, this is going to be equal to the real part of the integral from -infinity up to infinity of, well, it's going to be the same thing. So root 2y minus 1 over y squared plus 1 dy. But now we'd like to evaluate that using the complex analysis methods of contour integration. Okay, so let's get a picture of the contour that we'll use here. So here I'm going to focus on the upper half plane. And maybe right here, I'm going to put the number minus capital R. Over here, I'm going to put the number positive capital R. And then up here, I'll put I times capital R. So this is the real axis. This horizontal axis is the real axis. And then this vertical axis is the imaginary axis. And then the contour will be this semicircle, which is kind of built out of all of these parts. So let's maybe make this semicircle in this magenta color. Okay, so we have something like that. But let's notice that our integral is the limit of the semicircle that lives along the real axis. So that means we can write our integral as the difference in what's happening around the entire contour and, well, this extra arc here. Because if we take the difference of what's happening in the entire contour and the extra arc, we get what's happening along the real line. Okay, so let's write it like that. We have the real part, it's still in the real part, of the contour integral around this thing, which I'll call gamma r. And so let's maybe say this entire contour is called gamma r of, now I'm going to exchange y's for z's. So I've got the square root of 2z minus 1 over z squared plus 1 dz. And then from that, I need to subtract what's happening along this arc. So let's talk a little bit about what's happening along this arc. Maybe the best way to look at it is to parameterize the curve along this arc, which isn't too hard to do. So if we've got a value of z here, this value of z is of the form r times e to the I theta, and here theta will be somewhere between 0 and pi. Because that's the complex exponential way of parameterizing a top half of a circle. So that means I can just plug this value of z into our integral along this arc. So let's see, that's going to give us something like this. So we'll have I times, from doing our differential z component, which will produce our d theta. And so then we'll have the integral from 0 up to pi of, let's see, the square root of 2r e to the I theta minus 1 over r squared e to the 2I theta plus 1. And then this is d theta. So that's the parameterization of what's happening in this top arc. But now let's also recall that maybe an understood limit is existing right here. And maybe I'll put that coming out of this bit. And that's the limit as capital R goes to infinity. That's because we want this to take up the whole real number line in the end. But let's look over here and notice that in the end, the numerator of this looks like something of the form r to the 3 halves, whereas the denominator looks like something of the form r squared. And if you're letting r go to infinity, well, the denominator is going to win out and you'll get 0. So that's why in the end, we don't have to worry about this part of the integral, and we only have to focus on this bit right here. Okay, but let's notice that this bit right here has a 0 in the denominator, and that 0 occurs when z equals, well, plus or minus I. But the case when z equals positive I is the case that we need to worry about, because that's within the region bound by this curve. Okay, great. And so that's a so-called pole of this function. And now here's where we're going to use the Cauchy integral formula in order to evaluate this contour integral in terms of the residue at this pole. So this is going to be the real part, so we can bring that down. And then 2 pi I times the residue at z equals I, that's this pole here, of our function. So 2z minus 1 over z squared plus 1. Okay, so that last equality comes from, like I said, the Cauchy integral formula. Okay, but then this residue formula involves multiplying by z minus I and then taking a limit. And so in the end, we'll have the real part of 2 pi I, and then we'll have the limit as z goes to I of root z 2z minus 1 over z minus I, or sorry, z plus I. That's because the z minus I term canceled when we multiplied it in the residue formula. But now this is continuous at I, so we can just plug it in, and we'll have the real part of, let's see, 2 pi I times the square root of 2I minus 1 over 2I. But notice a 2 and an I cancel from the numerator and the denominator, and the pi can be brought out because it's a real number, and we get pi times the real part of 2I minus 1 under a square root. So now all that's left is to rewrite that in terms of a more well-known number. Okay, so via quite a bit of work, we've determined that our goal integral is equal to pi times the real part of the square root of 2I minus 1. Now, we'd like to rewrite that into something a little bit nicer to look at. So let's say that the real part of the square root of 2I minus 1 is equal to a. And so, like I said, that's a real number. But notice that that's equivalent to saying that the square root of 2I minus 1 is equal to a plus bi, where a and b are both real numbers. Because that's what we do when we extract the real part. We extract the real part. So from here we can square both sides. So squaring the left-hand side will obviously get rid of the square root, giving us 2I minus 1. Squaring the right-hand side using complex arithmetic, we'll get a squared minus b squared, and then plus 2abi. And now we can equate real parts. So notice minus 1 will be equal to a squared minus b squared, and imaginary parts. So 2 will be equal to 2ab to give us a nice system of equations. And that'll be b squared minus a squared is equal to 1. I just flip the sign there. And then a times b is also equal to 1. That's from dividing that by 2. But notice if a times b is equal to 1, that means that b is equal to 1 over a. But that's good because we can plug that into our other equation, and we've got an equation only for a. So note that we have 1 over a squared minus a squared is equal to 1. But then I can maybe multiply that again by 1 over a squared, and we'll get the following equation. So we'll have 1 over a squared quantity squared equals 1 over a squared plus 1. So that's after rewriting it a little bit. But let's notice that that means that 1 over a squared satisfies exactly the rules that define the golden ratio, meaning that 1 over a squared is equal to the golden ratio, but that means that a is equal to 1 over the square root of the golden ratio, just solving for a. But a was the real part of the number that we're looking for. So that means we can replace this real part of root 2i minus 1 with 1 over the golden ratio, giving us our final answer of pi over the square root of the golden ratio. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.